Welcome to Orbit Observer. Tonight I want to take you somewhere very small and very far away, out past the cold and the dark, to a place where two little worlds are quietly getting dressed. That is the strange truth we are going to sink into together, slowly, over the next while, so there is no rush at all. You can let your eyes close. You can let the day go. I will keep talking, and the story will keep unfolding, and if you drift off somewhere in the middle of it, that is exactly as it should be. So, let me begin the way this whole thing began for us, which is not with a photograph at all, but with a prediction. A guess made in the dark that turned out to be right. The year was 1990. A scientist named Mark R. Showalter was sitting with a set of old images, pictures that had already been sitting around for 9 years by then, taken back in 1981 by a spacecraft called Voyager 2 as it swept past Saturn. And in those images, Showalter was looking at one particular gap in Saturn's rings, a thin dark lane threaded through the bright outer ring, a gap called the Encke Gap, only about 325 kilometers wide, a narrow black ribbon running all the way around the planet inside the glowing band of ice. Now here is the part that I find so quietly wonderful, the part worth slowing down for. The edges of that gap were not straight. They were not clean. They had a soft, scalloped waviness to them, a gentle rippling, like the edge of a curtain that someone had just brushed past, or like the wavy trim along the edge of a pie crust pressed down by a thumb. The ring material along the border of the gap was drawn into little wave after little wave, a repeating scalloped pattern, and Showalter looked at those waves and understood that something had to be making them. Because waves like that do not just happen. Something had to be reaching out and tugging on that ring material, pulling it into those repeating ripples with the steady rhythm of its own gravity. Something was in there, keeping the lanes swept clear, brushing the ring dust aside as it went around and around. But no one had ever seen it. It was too small, too faint, hiding right there inside the very gap it was carving. So Showalter did the thing that still gives me a little chill of delight. He took the shape of the waves, the spacing of them, the way they marched along the gap edge, and he worked backward from that. He calculated, from the ripples alone, exactly where the hidden thing had to be. He did the arithmetic that the rings themselves were writing in their scalloped edges, and it told him where to look, and then he looked. And there it was. A tiny moon, exactly where the math said it would be. Astronomers knew precisely where this moon was before anyone had ever truly seen it, because the rings had already drawn its outline in the dark for them, in that soft, repeating wave along the gap. They named it Pan. I love that it works out that way, that you can find a whole little world you have never laid eyes on, simply by reading the ripples it leaves in the dust around it. Like knowing someone just walked through a quiet room because the curtains are still swaying. The moon was invisible, but its fingerprints were all over the ring, and a patient person read them. And so we have the first of our two little characters for tonight. Pan, a moon that lives inside a gap in Saturn's rings, not beside the rings, not above them, but genuinely down inside the ring material itself, in that swept clean lane called the Encke Gap. It orbits at a distance of about 133,584 kilometers from the center of Saturn. That is a number I will just set down gently here and not ask you to hold too tightly. What matters is the picture, a tiny moon, tucked inside a dark groove in a vast bright ring, going round and round, and by its very presence keeping that groove open. It is the sole reason the gap is there at all. Take Pan away, and the ring dust would drift back in and fill the lane. Pan keeps the door open just by being in the doorway. Now let me bring in the second one, because these two go together, and they will keep each other company all the way through this story. Some years before Pan, back in 1980, another scientist, Richard Terrell, had spotted a second little moon in images from Voyager 1, a different spacecraft, an earlier pass. This one did not live inside a gap. This one lived right at the very outer edge of Saturn's broad, bright A ring, sitting just past the ring's crisp outer boundary, out near a region called the Roche Division. It orbits a little farther out than Pan, at about 137,670 kilometers from Saturn's center. Again, a number to let float by, no need to grip it. This second moon seems to help hold that sharp outer edge of the ring in place, tending the boundary, keeping the ring's rim clean and defined. They named it Atlas. And already you can hear something lovely in the names, something the people who chose them meant on purpose. Pan, in the old Greek stories, was the god of shepherds, the one who tends the flock and keeps it gathered. And that is exactly what this little moon does. It shepherds the ring particles, herding them, keeping its lane clear, tending the dust like a flock. And Atlas was the Titan, condemned to hold up the sky on his shoulders forever. And this little moon sits right at the edge of the A ring and seems, in its quiet way, to hold up the ring's outer boundary to keep that edge from spilling outward. Two names. And both of them are about tending, about supporting, about caring for the rings. As if whoever named them already understood that these were not moons that simply happened to be near the rings. These were moons whose whole existence is bound up with tending the rings and, as we will see, with wearing them. So there they are, our two. Pan in its gap, Atlas at its edge. And I want you to understand just how small they truly are, because their smallness is the whole secret. And we will come back to it again and again tonight. These are not moons like the ones you might picture, not big round silver globes hanging in the sky. Pan is roughly 4 kilometers across in its longest direction and only about 21 in its shortest, a lumpy little thing, wider one way than another, with a mean size of maybe 28 kilometers. Atlas is a touch bigger, about 41 kilometers the long way and only 19 the short way, averaging around 30 kilometers across. To put that in the gentlest terms, these are worlds you could very nearly drive across in an afternoon if there were roads and air and any reason to. They are cities worth of ice and rubble, not planets. They are so small that if you stood on one, though you could not really stand, the gravity is so faint you would drift, you could throw a stone clean off it into space. And here is why that smallness matters so much. A world has to be fairly large before its own gravity can pull it into a smooth, round ball. Big moons are round because their gravity is strong enough to crush them into spheres, to pull every part of them down toward the center until they settle into that perfect shape. But something as tiny as Pan or Atlas has almost no gravity to speak of. It cannot round itself off. It has no power to smooth its own shape. So by every rule we know, these two little moons should be nothing more than irregular lumps, shapeless potatoes of ice and rock, cratered and dented, like almost every other small body of that size drifting through the solar system. They should look like broken things, like leftover rubble. And yet, and this is the enigma at the very heart of tonight, they do not. Because in 2017, when a spacecraft finally got close enough to see them clearly, The pictures that came back showed something that made scientists all over the world stop and stare and laugh out loud in surprise. These two tiny lumps, these two shapeless little worlds that should have been nothing but jagged rubble, each had something extraordinary wrapped around its middle. A skirt. A smooth, raised band running right around the equator of each moon. A neat, comparatively gentle ridge encircling the lumpy little body like a brim, like a rim, like the flared edge of a saucer. On Pan, that ridge is thin and sharp, and it juts out so cleanly that the whole moon ends up looking, and I promise you people really did say this, out loud, in the news, everywhere. It ended up looking exactly like a piece of ravioli, a little space dumpling. Some people said an empanada, some said a walnut, a lumpy core with a thin flared crust running all the way around the middle, pinched at the edge like pasta sealed shut. And Atlas, with its broader, smoother ridge, its wider brim, ended up looking like something else entirely. Like a flying saucer, like a little UFO. A classic domed disc, exactly the shape a child would draw if you asked them to draw a spaceship. A tiny white flying saucer drifting at the edge of Saturn's rings. And I understand completely why those were the words everyone reached for. Ravioli, flying saucer. Dumpling, walnut, they are affectionate, they are funny, they make these strange little worlds feel friendly and near. And that is where almost every telling of this story stops. It shows you the funny picture, it says the funny word, and it moves on, as if the whole point were the joke of the shape. But the shape is not the point. The shape is the clue. Because tonight, the question I want to lay down for us, the quiet mystery we are going to wander into together and let carry us off to sleep, is not what do they look like, it is why. Why does a tiny moon that cannot even round itself into a ball have a smooth, perfect ridge running exactly around its equator? Where did that neat brim come from if the moon has no gravity to shape itself? Something built that ridge. Something laid it down, right there around the middle, in a clean band, and nowhere else. And that leads us to the strangest and softest part of the whole thing, the piece I most want you to carry off to sleep with. That ridge is not part of the original moon at all. It is not the moon's own rock, worn or carved into a rim. It is something the moon gathered, something it collected, something it swept up out of the rings themselves and wore, piling it on, grain by grain, over an unimaginably long time, until the ring dust it had been ploughing through all those years had built it a smooth new equator out of nothing but settling ice. The rings made solid. The rings come to rest on the moon that lives inside them. Each of these little worlds is wearing a coat it scooped up itself, out of the dust it swims through, and the coat only ever settles in one place. Around the middle, right on the equator, exactly in the plane of the rings. Never on the poles, never scattered over the whole surface, only there, in that single thin belt. And that is the deepest part of the mystery, the thing I want to leave hanging softly in the air above us as we settle in. Why there? Why does the dust only rest in one place? Why can it not coat the whole little moon evenly, the way frost settles over a whole window pane? Why does every falling grain seem to know it is allowed to come to rest only in that one narrow band around the equator, and nowhere else at all? There is a reason. There is a beautiful, gentle, patient reason, and it has to do with exactly where these two little moons sit. Right at the delicate edge of what Saturn will allow to hold together at all. And we are going to walk our way slowly toward that answer over the course of tonight, one soft step at a time. I promise you, we will get there. But there is no hurry to arrive. The wondering is the good part. The wondering is what I want you to sink into. Before we go deeper, let me do one small thing, and then I will let the silence and the story take over. If you are lying somewhere in the dark right now, listening to this, I would love, whenever it suits you, for you to tell me where in the world you are. Just leave a little note in the comments, a city, a country, a time of night. I read them. There is something I find genuinely comforting about knowing that, all across the world, in all these different rooms, people are lying still and listening to the same quiet story about two tiny moons wearing skirts of ring dust. And if you are new here, if you have only just found this little corner of the night, you might gently hit subscribe so that the next slow story finds its way to you too, whenever you need something to help you drift off. That is all. No rush. You can do it now, or in the morning, or not at all. The story continues either way. So let us settle back in. I want you to picture Saturn, that great pale golden planet, hanging in the black, wrapped in its enormous flat rings. And the rings, remember, are not solid, they are not smooth bands of metal or ice, they are made of countless separate particles. Chips and grains and boulders of nearly pure water ice, uncountable trillions of them, ranging from specks of dust smaller than sugar to lumps the size of houses, all of them orbiting Saturn together, all lying in one impossibly thin flat sheet. If you could shrink the rings down to the width of a city block, they would be thinner than a sheet of paper. That flat, that delicate. A vast, shining, spinning disk of ice, hundreds of thousands of kilometers across, and yet so thin in the up and down direction that from certain angles it very nearly disappears. And embedded in that great flat sheet of ice, threading through it, going round and round, are our two little moons. Pan, tucked down inside its swept-clean gap in the outer part of the ring, and Atlas, right out at the crisp outer edge, just past where the bright ring ends. Both of them lying flat in that same plane, orbiting in the same direction as all the ring particles around them, moving through a slow, endless snow of ice grains that drift past them at only the gentlest of speeds, because everything out there is going the same way, in nearly the same circle, so nothing rushes. Nothing collides hard. It all just drifts along together, particle and moon alike, in one great patient river of ice. And these two moons move quickly, in their own way. Pan goes all the way around Saturn in only about 13.8 hours. Atlas takes a little longer, about 14.4 hours. So each of them laps that enormous planet roughly twice in a single Earth day. Round and round, again and again, sweeping continuously through the dust, brushing it aside, herding it, and, grain by drifting grain, gathering some of it up. They never stop. They have been going round like that, sweeping and gathering, for an amount of time that the human mind cannot really hold. Millions of years. Longer, round and round, twice a day. For longer than there have been eyes to watch them. And I find something so restful in that, in the sheer patience of it. There is no drama out there, no violence in this story, no crash, no catastrophe, just a tiny moon, moving slowly through a soft, endless snow of ice, and now and then a single grain drifting close, drifting closer, slowing, and finally coming to rest. One grain. And then, after who knows how long, another and another, each one settling gently onto the same thin belt around the middle, the only shelf where it is allowed to stay. A coat being put on so slowly that you could watch for 1,000 years and never see it thicken by the width of a hair. That is the pace of this story. That is the pace I want us to keep tonight. The pace of dust coming to rest. Now, I told you these are among the strangest-looking little worlds in all the solar system, and I want to add one more thing about how they look, because it feeds directly into the mystery. They are bright. They are astonishingly, brilliantly bright. White, among the most reflective bodies anywhere in the Sun's whole family of worlds. Most small moons, most little lumps of rock and ice, are dull and dark, grey or brownish, dimmed by ages of dust and radiation. But Pan and Atlas gleam. They shine like fresh snow, like clean bone, like something newly washed. And why? For the very same reason they have their skirts. Because they are constantly, endlessly being dusted with fresh, clean water ice out of the rings. The same slow snowfall that builds their equatorial ridge also keeps refrosting their whole surface with bright new ice, over and over, so they never have a chance to go dull. They are perpetually recoated in clean white frost, freshly laundered by the very rings they live in. The coat is not only a metaphor, their surfaces are, quite literally, made of ring ice come to rest, a clean white frosting laid down fresh, again and again, by the material they swim through. So hold that whole picture in your mind as you settle down. Two tiny moons, far too small to be round, far too small to have any real gravity of their own, lumpy little cores of ice and rubble, and yet each one wearing a smooth pale ridge around its middle and gleaming white all over, because it lives inside a great flat river of ice and has spent uncounted ages quietly gathering that ice onto itself. One with a thin, sharp brim, like a ravioli. One with a broad, gentle dome, like a little flying saucer. Both of them dressed in the rings, and the great soft question hanging over all of it, the one we will follow gently towards sleep. Why the equator? Why does the dust only ever rest in that one thin band? What rule, out there at the edge of what Saturn allows, decides that the grains may settle around the middle and nowhere else? We will get to the answer. It is a good one, and it is a kind one in its way. But not yet. For now I only want you to feel the shape of the wonder, to lie here in the dark and hold the image of those two little worlds, going round and round the great golden planet twice a day, patiently sweeping through the snow, patiently gathering their coats one grain at a time, gleaming white in the dark. Wearing the rings. Let me tell you a little more about how strange it truly is that Pan lives where it lives. Because most moons, even the little ones, orbit somewhere outside a planet's rings, or above them, or off to the side. They keep their distance. But Pan does not keep its distance. Pan is inside. Pan orbits within the ring, down in that swept-clean gap, embedded in the very sheet of ice it came from. It is one of the only moons in the entire solar system that can truly be said to live inside a ring rather than merely near one. It swims in the same ice it is made of and the same ice it wears. There is something almost tender about that when you sit with it. A little world drifting inside the material that made it. Still gathering more of that material onto itself, still being clothed by its own birthplace long after it formed. And all of it, the moon, the ridge around its middle, the ring it swims in, all of it lies in one single flat plane. That is the quiet thesis of the whole picture, the thing that ties it all together. If you could look edge-on at Pan, you would see the lumpy core, and the thin, bright skirt around its equator, and the wide, flat ring stretching away to either side, and the skirt and the ring would line up perfectly, the same flat plane threading straight through the moon's waist and out into the ring on both sides. The ridge is not tilted. It is not crooked. It lies exactly where the ring lies, in exactly the same plane, because it is the ring, come to rest. The skirt is a little piece of the ring that stopped drifting and settled down. Moon, ridge and ring, all lying flat together in one shining sheet. I want you to see that. To let that single flat plane run through your mind like a still, calm line. The moon at the centre, the ridge around its middle, the ring reaching out on either side, all of it level, all of it in one place, all of it quiet. And out at the edge, Atlas, doing much the same thing in its own way. A little broader in the brim, a little smoother, sitting right where the bright A ring ends and the emptier space beyond begins, at that crisp outer boundary, near the Roche Division, holding the edge in its Titan's way, gathering its own coat, gleaming its own white, wearing its own wider skirt of settled ring dust that gives it the round, domed shape of a little saucer resting on the dark. Two moons, two skirts, one made thin and sharp, one made broad and smooth. And already you might be wondering, if the same thing is happening to both of them, if both are just gathering ring dust onto their equators, then why do they not look the same? Why is one a ravioli and the other a flying saucer? Why two different shapes from one process? That is another thread we will follow, gently, later on. Another soft loop left open for us to close when we come to it. For now, just let it hang there with the rest, one thin brim, one broad dome. Same slow snowfall, two quiet outcomes. There is so much still to come, and I mean to take it slowly. We will look closely at that ridge, and at how we can be so sure it is gathered ring dust, and not the scar of some old collision. Because there is a beautiful piece of evidence hidden in the fact that the skirt lies exactly on the equator, and impacts, which come flying in from every random direction, could never lay something down so neatly in a single perfect band. We will meet the scientist Sébastien Charnoz, who built the careful model of how the ridge forms, and who gave it the loveliest name. He and his colleagues called these skirts the moon's terminal accretionary ornaments. Ornaments, as if the moons had dressed themselves up, as if the ring, in the end, had given each little world a piece of jewellery to wear. And we will come at last to the real answer to the question I keep setting down for you. Why the equator? Why only there? We will find that it has everything to do with how close these two moons sit to the very edge of what Saturn's gravity will permit to hold together at all, a delicate line called the Roche-limit, where the giant planet's pull is so insistent that anything venturing too near is stretched and pulled and never quite allowed to gather itself into a solid body. Pan and Atlas live right at that trembling edge, and it is precisely because they live there, right at the border of what is allowed, that the falling dust can only ever come to rest in that one thin equatorial band. The same delicate rule that lets Saturn's rings exist at all, that keeps all that ice spread out in a flat sheet instead of clumping into moons, is the very same rule that tailored these two little skirts. The rings and the ridges are made by one and the same gentle law. But all of that is still ahead of us, and there is no need to reach for it yet. We have a long, slow way to drift tonight, and I mean to fill it with soft details and gentle wonderings, and I will be here the whole way, keeping watch, keeping the story going, whether you are still awake to hear it or already halfway to somewhere else. For now, just rest with the picture. Saturn, pale and golden and enormous, wrapped in its impossibly thin sheet of shining ice. And down inside that sheet, threading through it, two tiny lumps of frost, and rubble, far too small to be round, going round and round the great planet twice a day, sweeping forever through a slow soft snow of ice grains, and gathering one grain at a time, without hurry, without violence, without end, a smooth pale coat around their middles, ravioli and flying saucer, shepherd and skyholder, two little worlds wearing the rings they live in, and the single grain of dust drifting closer through the dark, slowing, finally coming to rest on the only shelf where it is allowed to stay. And then, after a long, long while, the next. Let that be the rhythm you sink into. The rhythm of settling dust. Nothing to solve tonight, nothing to hold. Only two little moons, quietly getting dressed, out at the edge of what is allowed, in the soft, flat plane of Saturn's rings. And we are only just beginning to come close to them. And so let us come closer. Not all at once. There is no need to rush the approach, no reason to hurry the arrival. The moons are not going anywhere. They have been going round and round Saturn for a very long time, and they will still be going round when we get there, at whatever pace feels right, threading slowly through the dark and the glittering ice, until we are close enough to make out the shape of them in the light that falls, pale and even, from Saturn's disk. What you see when you finally get close enough is not what you expect a moon to look like. You expect something roughly round, or something jaggedly irregular, because those are the two shapes moons tend to come in. The large ones are round, pulled into spheres by their own gravity over billions of years, oceans of magma slowly settling, mountains slowly slumping, until nothing is higher than anything else, and the world has drawn itself into a ball. The small ones are not round at all. They are lumpy and elongated and pocked with craters, battered lumps of rock or ice that have never had enough mass to feel their own weight, never had the gravity to smooth themselves out. You have seen pictures of asteroids that look like this, like a potato left too long in the sun, or a misshapen stone a child might pick up from a riverbed and turn over in their fingers. Pan and Atlas look like neither of those things. They look, frankly, like something that has been added to, something that was one shape and then became another shape. Because something happened to it, something external and gradual and persistent. They look like they have been wrapped. And the more you look at the pictures, and the more you think about where these little moons live and what they have been doing all their lives, the more that impression of wrapping, of having been given a coat by something outside themselves, resolves from a vague visual feeling into a precise and verifiable fact. They were given a coat. The rings gave it to them. And the coat is still, in some sense, being put on. But let us take the shapes first, before the mechanism. The shapes are the most immediately legible thing, and they are worth sitting with for a moment before we start explaining them, because a good explanation should start with a genuine sense of what needs explaining. Pan first. Pan is roughly 34 kilometers long and 31 kilometers wide in its middle, and about 21 kilometers deep, so not even a perfect potato, more a flattened potato, a potato that has been pressed down a little from above and below. Its body, the old dense part of it, is cratered and irregular and dark in places, the way you would expect a small body in the outer solar system to look after billions of years of slow bombardment by debris. But around its middle, exactly at its equator, there is something else entirely. There is a ridge, a raised belt of material running all the way around the circumference of the little moon, smooth where the rest of the surface is rough, pale and almost unmarked where the body itself carries the history of old impacts. The ridge is not enormous. In absolute terms, it is a modest feature. not soaring high above the surrounding terrain, but it is distinct enough and coherent enough and sufficiently different in character from the rest of the surface that the eye goes to it immediately. And because Pan is roughly flattened and the ridge runs exactly around its widest circumference, the silhouette from the side is arresting. It does not look like a lump. It looks like a ravioli. It looks like a dumpling. It looks, as more than one scientist has said, like an empanada or like a walnut viewed end-on, the crimp of the shell running around the widest part. These are the names that circulated when the images came back: ravioli moon, walnut moon, space dumpling, and they are not wrong as descriptors of the silhouette, but they are, if we leave it there, almost completely useless as explanations, because a ravioli is the shape of something that has been folded and pressed by a hand, and the ridge on Pan was not folded and pressed by anything. It accumulated, it grew. It arrived, one tiny piece at a time, over an enormous span of time, settling from the rings onto the only place where settling was permitted. Atlas looks different. Atlas is slightly larger overall, roughly 41 kilometers long and 35 kilometers wide, with a depth of about 19 kilometers, so it too is flattened, compressed along the axis perpendicular to the ring plane, but its ridge is not a thin, sharp skirt at the edge of the body in the way Pan's is. Atlas's ridge is broader, more rounded, more smoothly integrated with the rest of the shape, so that the whole moon has a gentle, continuous swelling at the equator rather than a crisp, added-on fringe. The result is a shape that is less like a ravioli and more like a hat. A lens, a flying saucer, a lentil. The upper and lower surfaces curve gently away from the equatorial bulge, and if you were to look at a cross-section of Atlas from the side, you would see something very close to the classic silhouette of the UFO in old science fiction illustrations. A circular disk with rounded edges, a gentle doming above and below. People said UFO moon. They said flying saucer. They said the moon looks like something out of a bad movie from the 1950s. Except that it is real, and it is made of ice, and it is orbiting Saturn, and it is only 30 kilometers across. Same mechanism. Different shape. The reason for the difference is something we will come to, but hold that question for now. Let it settle somewhere just beneath your attention, where unanswered questions tend to be most useful when you are trying to sleep, because they give the mind something soft and specific to rest against without demanding immediate resolution. The point, for the moment, is simply this. Both moons have a raised ridge of material running around their equators, precisely in the ring plane, and the ridge looks different from the rest of the surface. And different in the same ways on both bodies. Smooth, where the rest of the surface is cratered and rough. Pale, where the rest is darker and older. Low in profile relative to what you might expect if the material had been thrown on suddenly, not a violent heap but a gentle belt, as though laid down over time by something patient. And aligned in both cases to the equator with a precision that is itself a kind of argument. A kind of evidence, if you know what to look for and know what the alternative explanations would predict. Because there is an alternative explanation that suggests itself immediately, and it is worth naming it, if only to set it aside carefully. The obvious thing to think, when you first look at an irregular small body and see a raised belt of material around its middle, is that the material was thrown there by impacts. Small bodies in the solar system are constantly being hit by smaller debris, and when something hits a surface at high speed, it does not just leave a crater, it throws material outward in all directions. and some of that material comes back down and settles. Perhaps the ridges are nothing more than accumulated impact ejecta, crater debris that happened over billions of years to pile up around the equatorial region. It is a reasonable thing to think, but it does not survive contact with what we actually see. Consider first the alignment. Impact debris does not land at the equator. Or rather, it does not preferentially land at the equator any more than anywhere else, because impacts come from random directions, from debris moving on all sorts of different trajectories, and the debris they throw lands on a small, irregular body, more or less uniformly, distributed over the whole surface, not concentrated in a thin belt. If you want to produce a perfectly equatorial ridge from impact ejecta alone, you need a mechanism that channels all the incoming projectiles and all the outgoing debris to one specific latitude, and no such mechanism exists. The equatorial alignment is not what impact ejecta produces. Impact ejecta produces, over long timescales, a relatively uniform coating, or in specific cases, a local enhancement near a large crater, but not a clean belt running with such precision along the equatorial plane that it is essentially indistinguishable from the plane of the rings themselves. Consider then the smoothness. Impact debris is rough. Craters are rough. The material thrown from craters is irregular, chunky, variable in size, and when it settles it produces a surface that carries its own small craters, its own texture, its own geological history of being hit. The ridges on Pan and Atlas are smooth, not slightly smoother than the body, markedly, strikingly smoother in the images that came back from the close passes. The ridge on Pan, in particular, is so smooth in comparison to the cratered terrain of the underlying body that it reads almost immediately as a different material entirely, deposited by a different process. Fine-grained, gentle, laid down rather than thrown down. And consider the relief. If a ridge were built up by impact ejecta over billions of years, it would carry within it a complex layered history of bombardment, and it would tend to be deeply irregular in height, built up in places, worn down in others. The ridges on these moons are low in relief relative to the body's overall dimensions, and comparatively consistent in height around the circumference. They do not look like something that accumulated randomly. They look like something that was deposited by a process that was acting uniformly, all the way around. All of that, the alignment to the equator, the smoothness, the low and consistent relief, points in one direction. These ridges are not made of impact debris. They are made of material that arrived from the rings, drifting in on the ring plane, settling with extraordinary gentleness onto the equatorial belt of a moon too small to hold it anywhere else. The ridge is ring material. It is made of the same fine water ice grains that make up the rings themselves, and it got to the equator of the moon in the same way that a light snowfall gets to the ground. Not violently, not suddenly, but slowly, in the dark, one flake at a time, over more time than is easy to imagine. This is not a guess, and it is not just a logical inference from the visual evidence. It is a model, a specific, published, peer-reviewed model with names and a year and a journal attached to it, and the model has held up to scrutiny in the years since it was proposed. The name to remember is Sébastien Charnoz. In 2007, Charnoz and his colleagues published a paper in the journal Science in which they proposed a detailed explanation for the equatorial ridges of Pan and Atlas. And the word they used, the word the researchers themselves chose in a scientific paper to describe these ridges, was ornament. They called the ridges terminal accretionary ornaments. Terminal, meaning that the process had largely run to completion, that the ridge was a record of something mostly finished, a nearly final coat. Accretionary, meaning that the material had been added on, had accreted, had gathered grain by grain from outside the moon rather than being part of the original body. And ornament. Not structure, not feature, not geological formation. Ornament. There is something very particular about that word. An ornament is something added to something else for the purpose of beautification, or as a mark of identity, or as a record of belonging, a brooch pinned to a coat, a garland draped across a doorway, a ring of flowers worn around the head at a festival. The scientists use that word deliberately, or at least with enough awareness of its implications to let it stand in a published paper, and I think they were right to use it, because what Pan and Atlas are wearing around their equators is, in the most literal available sense, an ornament of the rings. The rings decorated these moons. The rings gave them the only adornment they have. The mechanism the model describes works in 2 stages. In the first stage, long ago before the ridge was anything, there was a core. A dense, irregularly shaped lump of material, probably a shard or a remnant of something larger that was once disrupted, perhaps by an impact, perhaps by the tidal forces of Saturn itself acting on a body that wandered too close, breaking it apart and leaving fragments orbiting in the ring plane. The precise origin of the dense inner cores of Pan and Atlas is not fully settled. That is a question the science holds honestly open, but what is reasonably well established is that the cores are old and dense and irregular, the kind of lumpy potato shape you might expect from a fragment of rock or ice that has never been smoothed by gravity. This is the first stage. The core exists, orbiting inside or near the rings, its surface rough with the history of impacts, its shape arbitrary and irregular. In the second stage, the coating begins. And this is the stage that takes the time, and this is the stage that makes the ridge. Ring material, fine grains of water ice, the same stuff the rings themselves are made of, drifts toward the moon on nearly circular orbits. Because the moon is in the ring plane and the ring particles are in the ring plane, the incoming material approaches from the equatorial direction, from the same flat disk in which everything in this part of the Saturn system lives. The particles are moving at very low relative velocity to the moon, because they are in nearly the same orbit, going around Saturn at nearly the same speed, just slightly inside or outside the moon's path, and so when they encounter the moon's gravity, they do not arrive like projectiles, but like something more nearly settling, like dust drifting down in still air, arriving with so little energy that they do not bounce away or excavate a crater, but simply stop. They come to rest. And here is the part that is, I think, the most quietly beautiful detail in the whole mechanism. They can only come to rest in one place. The moon is, by the standards of anything large enough to be called a moon, extraordinarily small. Its gravity is very weak, and it is embedded in the gravitational field of Saturn, which is enormously strong by comparison. And the combined effect of Saturn's gravity and the Moon's gravity and the Moon's orbital motion around Saturn produces a situation that planetary scientists describe in terms of something called the Roche-limit, or, in this specific application, the Roche critical density. You do not need to understand the mathematics of it in detail to understand the outcome, which is this: there is a region around the Moon's equator, lying exactly in the ring plane, where an incoming particle's orbit can be gently deflected by the Moon's gravity, and the particle can settle onto the surface and stay. Everywhere else on the Moon's surface, the geometry of the gravitational fields, Saturn pulling one way, the Moon's own weak gravity pulling another way. The orbital motion adding its own complicating pull means that a particle that tries to come to rest there will eventually be tugged away again, or will not be captured at all. The poles are inaccessible. The higher latitudes are too strongly competed for by Saturn's tidal forces. Only the equatorial belt, lying in the same plane as the rings and the particle's own orbit, is sheltered enough, geometrically stable enough, for the material to stick. It is, in a sense, like a shelf. Saturn's tidal gravity reaches in and tilts the Moon's effective gravitational landscape so that the equator is the lowest point, the place where anything loose will eventually roll to and stay, and the poles are the high ground that nothing can hold on to. The fine ring particles, drifting in from the disk, naturally find that shelf and come to rest on it. And there they stay, and more arrive, and slowly, over a span of time that we cannot easily put a human number on, but that is certainly millions of years, and probably much longer, the shelf accumulates material, and the material becomes a ridge. And the ridge grows until it has roughly swept clean the orbital lane nearby, and there is very little new material left to arrive. Terminal, the ornament is nearly finished. The skirt has been sewn. Now think about Richard Terrell for a moment, and Mark Showalter, because the discovery of these moons is itself a kind of story about patience and looking carefully at things that other people have looked at before. Richard Terrell was working with the images that came back from Voyager 1 in 1980, when that spacecraft made its close approach to Saturn and sent back the first detailed pictures humanity had ever taken of the ring system. Voyager 1 did not have much time at Saturn. It was moving fast. It was on its way somewhere else. The flyby was brief by the standards of the science you could do with it. And yet among the enormous archive of images that came back, Terrell found, tucked in near the outer edge of the A-ring, a small, faint, previously uncatalogued body. He found Atlas, a moon nobody had known was there. Not because it was hidden in any dramatic sense, but because you had to look carefully, and carefully was exactly how Terrell was looking. Atlas was a discovery made by attention, by someone sitting with a set of images and looking at them more methodically than the urgency of the moment might have seemed to require. Pan was different. Pan was a discovery made before it was a discovery at all. It was a prediction first and a confirmation second. Voyager 2 flew past Saturn in 1981, a year after Voyager 1, and sent back its own archive of images. Among those images were pictures of the Encke Gap, the broad clearing in the A-ring where Pan lives. And those images showed something odd about the gap's edges. The boundaries of the gap were not clean and smooth. They were wavy. They were scalloped, as though something invisible were running along inside the gap and tugging at the ring material on either side as it passed, raising ripples and curls in the edge of the ring, the way a boat raises a wake in water. And here is the beautiful thing. The rings themselves are a recording medium. They register the gravity of things that move through them, and they hold the record in their own structure, in the shapes of their edges, in the fine wavy patterns that propagate outward from anything massive enough to tug. The Encke Gap's scalloped edges were a record of something moving through it, something that had not been seen, but whose presence was written in the ice. Mark Showalter read that record. In 1990, working with Voyager 2 images taken 9 years earlier, Showalter calculated where the invisible body causing those wavy gap edges had to be. He computed its orbital radius, its orbital period, its approximate mass, from the pattern of disturbances in the ring alone, and then he searched the images for a tiny point of light at the predicted location. And he found it. There was Pan, orbiting inside the Encke Gap, right where the rings had told him it would be. The moon was discovered not by seeing it, but by reading the disturbance it had left in the rings around it, the way you might know a ship passed through a harbour by the waves still moving on the water when you arrive, long after the ship itself has gone. Except that Pan, of course, had not gone anywhere. It was still there, still making those waves, still running loops around Saturn inside its gap, waiting to be confirmed. There is something in that story that is worth dwelling on, at whatever pace feels right, in the dark, with Saturn somewhere out beyond the frame of the window. The idea that a moon can be known before it is seen, that the absence of a body can be as eloquent as its presence, that the rings themselves, going about their slow and patient business, were carrying a message that only needed someone with the right knowledge and the right patience to read. The rings told us Pan was there. The rings drew its outline in the dark, long before any human eye confirmed it. And then, of course, Pan's outline turned out to be a ravioli. There is a thing about Pan, in particular, that is easy to overlook when you are thinking about the shape of it and the mechanism that produced the ridge, and it is this: Pan is not orbiting near the rings, or beside the rings, or in the gap between rings. Pan is orbiting inside a ring. Pan is embedded in the A ring itself, threading the narrow corridor of the Encke Gap, which is a clearing in the ring but is still, in every meaningful sense, part of the ring system. The A ring extends all around it, the ring material extends all around it, and Pan moves through that material continuously, every 13 hours and a bit, every day, every year, every million years. There are very few moons in the solar system that can claim this, that their home is not beside a ring or in the vicinity of a ring, but inside one, genuinely inside it, orbiting within the material that the ring is made of. And what that means for Pan is not just that the Encke Gap stays open because Pan is there, herding the ring material away from its path. It also means that Pan has never, in all its history, been anywhere else. It has never orbited in empty space, clear of the rings. It has been threading this same corridor, surrounded on both sides by the ring, for as long as it has been Pan. And the material of the ring has been drifting toward it for all that time, arriving gently at the equatorial shelf, settling, one grain of ice at a time, onto the only place where it could stay. Pan has been, from its beginning, in the process of becoming what it is now, not finished, not static. A moon in the act of being made, slowly, by the medium it moves through. That is an unusual thing to be. Most worlds are not in the act of being made. Most worlds formed long ago in a relatively brief and violent period of early accretion, and have been slowly changing since, but not in any sense actively accumulating new material in a coherent way. Pan is different. Pan is still receiving its coat. The coat is mostly on, the process is largely complete, which is part of what Charnoz's model means by terminal, but it has not stopped. New ring material still arrives, still settles, still adds, infinitesimally slowly, to the equatorial ridge. Pan is a moon that has been in the process of being dressed for millions of years and is still, in some small sense, being dressed tonight. Atlas is less deep in the rings than Pan. Atlas orbits just outside the A ring's outer edge, in the region near the Roche Division, the gap between the A ring and the faint F ring beyond. So Atlas is not embedded in the ring the way Pan is, but rather sits just at the boundary, just at the lip, where the ring's material reaches, but the ring's full density does not. This is part of why Atlas's ridge looks different from Pan's. Atlas was never as completely surrounded by ring material as Pan. The material it collected came predominantly from the ring's outer edge, which meant the supply was somewhat different, somewhat more limited on certain sides, and the ridge that resulted is broader and smoother and more completely merged with the underlying body. The way a coating that goes on more thickly and more slowly can become indistinguishable from the surface beneath it, while a thinner, more delicate coating retains its separate identity as a layer. Both ridges, though, are made of the same thing. Both are water ice. Both are bright. Extraordinarily bright, in fact, among the brightest surfaces in the solar system, which is a thing worth pausing on, because it tells you something important about how recently the coat was applied. Old ice, ice that has been sitting on a surface for billions of years, is not white, it is dark. It gets darkened by radiation, by the slow bombardment of charged particles and cosmic rays and ultraviolet light, which break apart water ice molecules and leave behind dark organic residues, a slow tanning of the surface over geological time. The moons and satellites of the outer solar system that have been sitting exposed for a very long time tend to have dark surfaces, or at least surfaces that are much less reflective than freshly deposited ice. But Pan and Atlas are bright. They are among the most reflective bodies known in the solar system. Their surfaces bounce back an enormous fraction of the sunlight that reaches them, which means their surfaces are covered in fresh, clean, unirradiated water ice, which means the coat is new, at least on the geological timescale, which is entirely consistent with the idea that these ridges are not ancient, battered, radiation-processed remnants, but rather freshly deposited ring material, still being laid down, still arriving, still as bright as the rings themselves. Because it is the rings themselves, or was, before it settled and stopped moving, and became, slowly and quietly, the outermost layer of a moon. The coat is fresh, the ornament is still shining. And then there are the densities, which are, in their way, the most surprising thing about these two small worlds, more surprising even than their shapes. Pan has a bulk density of approximately 0.42 grams per cubic centimeter. Atlas has a bulk density of approximately 0.46 grams per cubic centimeter. These are not numbers that mean very much in isolation, but they become very striking when you place them alongside the density of water, which is 1 gram per cubic centimeter exactly, by definition. Pan is less than half as dense as water. Atlas is less than half as dense as water. Put either of these moons in an ocean large enough to hold them, and they would float, with room to spare, lighter than ice, lighter than the rings themselves, which are mostly water ice, which itself has a density of about 0.9 grams per cubic centimeter. Pan and Atlas are less dense than the material they are made of, which seems, on its face, impossible. Until you understand that density is not just about what something is made of, but about how it is put together. And what the very low densities of Pan and Atlas are telling you is that they are not solid. They are not dense packed rock and ice with no spaces. They are porous. They are rubble, loosely assembled, held together by their own very weak gravity, and by the gentle compression of the ring material piled on their equators, full of gaps and voids and air pockets, more foam than stone in the structural sense, though made of ice rather than soap. And that too is consistent with the accretion story. A moon built by gently drifting particles arriving at low velocity and settling onto a surface without violence is not going to be densely packed. The particles do not arrive with enough energy to compress the material beneath them significantly. They come to rest in whatever configuration they happen to fall into, like a very slow and very cold snowfall, and the result is a porous, fluffy structure. The kind of structure that has a lot of nothing in it, a lot of space between the grains, a lot of emptiness woven through the apparently solid form. Pan and Atlas, in a sense, are mostly space. They are structures made of ice, with large amounts of void distributed through them, and the low densities are the record of how gently everything arrived. There is something restful about that. Something that resonates if you are lying in the dark and trying to let the thoughts loosen and drift apart. The idea that a world can be mostly space, that something that looks solid from the outside, that holds a consistent shape and follows a precise orbit and casts a shadow in Saturn's light, can be, at the level of its actual physical structure, more empty than full, mostly gap, mostly dark between the grains. A thing held together not by the compression of its own weight, but by the patience of time and the gentleness of everything that arrived. So hold that image for a moment, if you will. A moon that is mostly space. A moon that is mostly the memory of arrivals, each one so gentle that the thing that arrived is still sitting almost exactly where it landed, barely compressed, barely disturbed, the structure around it barely altered by the weight of everything that came after. And now ask the question that has been waiting beneath everything said so far, the question that the shape of these two little moons insists upon if you look at them long enough. Why the equator? Because that is the real mystery when you settle into it. Not simply that the ridge exists, that material accreted, that dust drifted in and came to rest, but that it came to rest in exactly one place. And that place is so precise, so geometrically perfect, so entirely unrandom, that you cannot look at it without knowing something deliberate is happening. Or not deliberate, because nothing about this is intentional, nothing is chosen or willed or decided. But something is enforced. Something in the physics of this particular region of space around Saturn makes the equator the only place the material is allowed to settle, and everywhere else, the polar regions, the mid-latitudes, any surface that tilts away even slightly from the ring plane, is effectively forbidden. Think about what it would look like if the accretion were random. If ring particles arrived from all directions, at all angles, coating every part of the surface the way frost coats a window, then Pan and Atlas would not look the way they do. They would be roundish lumps, irregular and bumpy perhaps, but covered uniformly, frosted all over, no single feature that drew the eye and announced itself as different from the rest. They might look something like Daphnis, the smaller moon in the Encke Gap, or something like Prometheus, or like any of dozens of irregular moons elsewhere in the solar system that accumulated material without a strong geometric constraint on where it was allowed to go. They would be odd little objects, no doubt, but they would not have that unmistakable profile, that raised belt, that smooth skirt, that rim running around the middle like something a careful hand had pressed there, and yet they do have it. Pan's ridge is thin and sharp, a narrow collar barely wider than the core beneath it in the narrow dimension, giving that famous walnut or ravioli profile, a compact central body pinched at top and bottom by the protruding skirt running around the middle. Atlas's ridge is broader, more generous, the skirt spreading wider relative to the core and giving that flying saucer or UFO appearance, a flattened disk with a swollen equatorial bulge that seems to overflow the central mass on all sides. Different in width, different in profile, but both sitting right at 0 degrees latitude, both lying flush with the ring plane, both telling the same story in different proportions. The physics that produced this is called, in the technical language, Roche critical density. And the Roche limit, more broadly, is one of the organizing ideas of ring science, one of the facts about gravity that explains why rings exist at all, why a moon can form here but not there, why material in one region piles into solid bodies and material in another stays strewn out in a flat, glittering sheet. The Roche limit is a boundary in space, not a line drawn on a map, but a threshold in the physics, and it exists because of what happens to a loosely bound object, a collection of particles held together by their own gravity, when it gets too close to a much larger body. An everyday way to think about it. Imagine you are holding a pile of sand loosely in your hands, and you are standing far from a very strong magnet. The magnet pulls on all the grains equally, more or less, because they are all at roughly the same distance. The pull is even, it does not tend to pull the grains apart from each other, and the pile stays a pile. Now move closer. And closer. When you get close enough, the magnet is pulling significantly harder on the grains nearest to it than on the grains farthest from it. Because those nearer grains are closer, and gravity, like magnetism, falls off with distance. This difference in pull, this tug that is stronger on one side of your pile than the other, is called a tidal force. And if the tidal force gets strong enough, it overcomes whatever holds the pile together, and the pile is pulled apart. That is what happens to a loosely bound body inside the Roche limit. Saturn's gravity is not the same at every point in space around it. It is stronger closer in, weaker farther out. A moon has material on its near side which is being pulled toward Saturn a little more strongly, and material on its far side which is being pulled a little less strongly. This differential, this gradient, tends to stretch the moon, to elongate it toward and away from Saturn, to try to pull it apart along the line connecting the moon's center to Saturn's center. For a small, weak moon with not much gravity of its own, the tidal stretch can be strong enough to prevent the moon from accumulating too much material, because any large pile-up would just be pulled apart again. This is why the rings exist. Inside the Roche limit, material cannot easily clump into a large moon. The tidal forces shear it apart or prevent it from accumulating in the first place, and so it remains spread out in the flat, thin sheet we see as the rings. Outside the Roche limit, material can clump. Self-gravity can win over tidal disruption, and moons form. The exact radius of the Roche limit depends on the density of the material involved. Denser material has stronger self-gravity and can hold together closer in. Less dense, fluffier material has weaker self-gravity and gets tidally disrupted at a greater distance. Pan and Atlas are right at the edge of this zone. They are not comfortably outside it, where gravity holds everything together easily and moons grow freely. They are right near the inner edge of the transition region, where the physics is delicately balanced, where the tidal forces from Saturn are strong but not quite strong enough to prevent any accretion at all, where material can pile up but only under precise conditions. Only in the specific geometry where the tidal disruption is weakest. And where is the tidal disruption weakest on a moon in this region? At the equator, at the ring plane. Here is why. The tidal stretch, the differential pull that tries to pull the moon apart, acts along the direction toward Saturn. It tries to elongate the moon radially, toward and away from the planet. In the ring plane, at the equator, material sitting on the surface is already aligned with this stretch. It is in the plane of the moon's orbit, moving at roughly the same speed as the moon itself, arriving on nearly circular paths. The relative velocity between a ring particle and the moon's equatorial surface, at the moment of closest approach, is very small. The particle drifts in gently. And in this geometry, the tidal force does not try to pull the settled material away from the surface. Instead, it sort of presses things together, or at least does not strongly oppose the accretion. Away from the equator, the situation changes. A particle trying to settle at high latitude on the polar regions of the moon would have to be moving at a different angle, a different inclination. It would need more energy to get there. Or it would arrive at a higher relative velocity, or the tidal forces at that geometry would more effectively oppose the settling. The moon's own weak gravity, and these moons have very little of it, given their small size, is not strong enough to pull in material from off-plane, not at the tidal stresses present in this region. The equatorial belt is the path of least resistance. It is the only shelf the physics allows. So the ring particles, drifting in on their nearly circular orbits in the ring plane, at their low relative velocities, find the equator of Pan and the equator of Atlas, and they settle there. Grain by grain, over millions of years, the equatorial ridge grows outward. Not violently, not in a rush. At the pace of the slowest possible accumulation, each particle a tiny addition to the rim growing outward like the edge of a saucer being widened one careful press at a time. This is what Sébastien Charnoz and his colleagues captured in their 2007 model. The model that used the word ornament, that patient outward growth in the plane, the ridge not cutting into the core but adding to its circumference, building new equator where there had been none. And the word terminal in their description, terminal accretionary ornaments, speaks to the fact that this process runs toward completion, that there is a limit to how much material the physics allows to pile there, and that Pan and Atlas have likely reached or nearly reached that limit. The skirts are in some sense finished, or nearly finished. The lanes have been swept relatively clean, the material that was available in those immediate regions has been largely gathered in, and what you see in the Cassini images is the record of a process that ran most of the way to its end. That is worth sitting with. The ridge is not a work in progress, not a thing still actively accumulating at a rapid pace. It is more like a completed structure, a record of all the settling that happened over the vast expanse of time since these cores first formed and began their patient gathering. It is the history of millions of years of slow accumulation, written in the shape of a smooth white belt around two tiny moons, each orbit of each moon around Saturn bringing the same ring plane into contact with the same equatorial surface, each contact an opportunity for a few more grains to find their shelf and stay. Pan completes one full orbit of Saturn in approximately 13.5 hours. 13.8 hours, approximately less than a day. Atlas takes a little longer, approximately 14.4 hours. So, in the time it takes for a full day to pass on Earth, 24 hours, Pan has swept all the way around Saturn through the full width of the Encke Gap, nearly twice. 2 full circuits, 2 complete passes through the ring material, 2 sweeps of that equatorial collector through the available dust. And this has been happening, orbit after orbit, for an enormous span of time. Not for years, not for centuries, but for timescales that dwarf everything we normally think about, timescales on which even the very slow accumulation of ridge material becomes substantial. Orbit by orbit by orbit, at 13.8 hours each, the equatorial shelf of Pan has been meeting the ring plane. Each meeting a contact, each contact a chance for something to settle. Most passes yield almost nothing measurable. But over millions of years, the nothings add up. The rim builds. The smooth white belt thickens and widens, very, very slowly, until it becomes the shape that the Cassini spacecraft photographed in the early months of 2017 and sent back as one of the last detailed portraits it would ever take of these two small worlds. And the brightness of the ridge, the extraordinary reflectiveness, is itself a record of how fresh this accreted material is in the geological sense. The fine water ice that coats Pan and Atlas, that refrosts their surfaces continuously, has not had time to darken. Ice exposed in space for long periods tends to accumulate organic compounds, to be irradiated by charged particles, to pick up dust that is not clean and white, but various shades of brown and grey. This darkening is called space weathering, and it happens to nearly every surface in the outer solar system over sufficient time. But the surfaces of Pan and Atlas are not dark. They are bright white, almost startlingly reflective, among the most reflective small bodies in the solar system. The reason is that they are always being freshly coated. The ring material raining down on the equatorial ridge is clean, new, bright water ice, the same material that makes Saturn's main rings among the most reflective structures in the solar system. And because Pan and Atlas orbit inside and at the edge of those rings, because they are in constant contact with that clean material, their surfaces are being renewed faster than space weathering can darken them. They are perpetually fresh, perpetually refrosted, perpetually bright. The coat they wear is not old and weathered, it is constantly replenished, new ice settling on top of old, the brightness maintained by the same process that built the ridge in the first place. Imagine a window that frosts over in the cold, and you keep breathing on it, and the frost is always there, always white and bright, never cleared for long, because the conditions that create it are always present. That is something like the situation for Pan and Atlas. The ring material is always there. The equatorial geometry is always there. The settlement is always happening, even if the main architectural work is largely finished, even if the ridge is not growing much taller or wider now. The surface is still being touched, still being whitened, still being maintained in its extraordinary brightness by the same patient physics that built it. And then there is the grain structure. The way Pan's ridge, looked at very carefully in the finest Cassini images, seems to show subtle layering, not the obvious banding of something like sedimentary rock, nothing as dramatic or clear as that, but hints of structure within the ridge material that suggest it was not deposited all at once, not accumulated in a single episode, but laid down in successive phases. Subtle grooves or variations in the surface texture that might mark different periods of more or less active accretion, different epochs in the moon's long history of gathering. The coat was not tailored in one sitting. It grew gradually, layer by subtle layer, each layer a period of settling, each period part of the long, slow account of time passing and material drifting in. This is harder to read than the gross shape of the ridge. It is at the edge of what the Cassini images can resolve, at the level of interpretation rather than definitive measurement. But it fits. It fits with what you would expect of a process that runs over millions of years and responds to the changing conditions of the ring environment over that time. The rings themselves are not perfectly static. They are perturbed by resonances with larger moons farther out. They have regions of varying density. They have their own complex dynamics. And those variations would be recorded, faintly, in the structure of the material that settled out of them onto Pan's equatorial ridge. The moon as a slow recorder of ring history. The coat as an archive. The ring plane. The orbital plane. The equatorial plane of the ridge. These are not three separate things. They are one thing, a single flat geometry threading through everything in this system. The sheet of ring material, the orbits of Pan and Atlas as they move within and beside it, the ridge that grew in that plane. The shared flatness that connects moon and ring and coat into a single continuous structure. This is, in a sense, the visual thesis of the whole story. When you see the image of Pan, when you look at that sharp-edged ravioli shape, you are not seeing a moon that has been decorated, not seeing something that has been altered from the outside by a force that came from elsewhere. You are seeing a moon and a ring that are part of the same thing, part of the same flat structure, the moon a local concentration of mass within the ring, and the ring returning the gift by settling onto the equator of the moon, filling in the plane right there at the moon's middle, building an equatorial shelf that is, geometrically and physically, a piece of ring made local, made solid, made part of the small world, rather than floating freely in the sheet around it. Pan orbits inside the Encke Gap. Not beside it, not near it, inside it. It is embedded in the ring material, surrounded by the edges of its own gap, sweeping through the region that it cleared and that it continuously tends. And the ridge on its equator is made of the same material as the ring walls around it. The moon and the ring are not separate objects in separate categories. They are the same system, different phases of the same inventory of material. The ring the diffuse phase, and the moon the concentrated phase, and the ridge the ongoing process of transfer between them, material leaving the diffuse phase and entering the concentrated phase, the ring becoming moon. Not quickly, not dramatically, but steadily, patiently, in the only geometry the physics permits. It is a deeply quiet image, a deeply quiet idea, not explosive, not catastrophic, not violent in any way. Ring becoming moon, a grain at a time, over timescales so long that the word slow barely captures them, in a flat plane so precisely maintained that the ridge it builds is essentially a geometric line around the equator, not a broad smear, not a lumpy accumulation, but a precise belt, exactly at zero latitude, exactly in the ring plane, exactly where the physics said the only available shelf was. If you were going to design a process to be as restful as possible, as unlike the violent origin stories of most solar system objects as possible, you might design something like this. The most common story about how moons and planets and small bodies are shaped by impacts, by rocks arriving at high velocity, by collisions that excavate and scatter and heat and sometimes shatter, is a story about violence, about the cosmos as a place of energetic catastrophe, which is accurate but not the whole story. There is also this. There is the drift, the patient, geometrically governed arrival of very small things moving very slowly, settling on the only surface they are permitted to settle on, accumulating not through force but through opportunity. The opportunity of a shelf in the right place, at the right geometry, in the right physical regime. Pan and Atlas are the result of both stories. Their cause, the dense central bodies around which the ring material accreted, came from somewhere older, from some earlier phase of the ring system's history, possibly shards of something larger that disrupted, possibly primordial condensations from the very early solar system's ring material. The origin of the cores themselves is not fully settled. That question remains somewhat open, and it is honest to acknowledge it as open rather than to present a neat answer the science does not yet fully support. But the coats, the ridges, the smooth white skirts, those are well understood, or at least well modelled, and the model is clear. The coat is ring material, settled in the ring plane, built outward from the equator by the patient geometry of the Roche-limit, over time so long it makes the whole of human history look like an afternoon. And the result of that patience, the visible, measurable, photographable result, is a moon less dense than ice, white as fresh snow, with a smooth belt running around its middle that is precisely aligned to the sheet of ring material it spent its long history gathering. The densities confirm the gentleness. Pan at approximately 0.42 grams per cubic centimetre, Atlas at approximately 0.46 grams per cubic centimetre, both well below the density of water ice, which sits at about 0.92 grams per cubic centimetre, well below solid rock of any kind, below even the density of many porous ices and compacted snows. These are not merely light objects, they are extraordinarily light objects. Objects with a great deal of empty space woven through them. Objects whose internal structure is more foam than stone, more gap than grain, more void than solid. The fact that these moons exist at all, that they hold together at all in this tidal environment near the Roche-limit, is itself a testament, if you will permit the word, to the delicate calibration of the physics. A little denser, and they would hold together more firmly, and might have gathered more material. A little less dense, and Saturn's tidal forces might have disrupted them. As it is, they sit near the threshold, holding their shapes, maintaining their gaps, wearing their white equatorial skirts, each orbit carrying them once more through the ring plane, each pass adding its infinitesimal contribution to the patient record. 13.8 hours for Pan to circle Saturn. 14.4 for Atlas. In a single Earth day, Pan sweeps that equatorial collector through the ring environment nearly twice. In a year, approximately 630 times. In a million years, 630 billion times. Each pass a contact, each contact a chance. Most of them yield almost nothing. Some yield a grain, or a cluster of grains, or a very faint increase in the mass of the ridge. Over millions and millions of years, the nothings add to the shape you saw in the Cassini images of 2017, that clean, white, geometrically perfect equatorial belt on a tiny moon hurtling through the dark at the edge of Saturn's rings. The shared plane of ring and ridge and orbit is, in the end, the deepest thing about Pan and Atlas. It is what makes them different from almost any other small body in the solar system. Nearly everything else is shaped by what hit it, by the random, direction-agnostic violence of impacts that can come from any angle and leave their marks anywhere on the surface. Pan and Atlas were shaped by what settled on them, and what settled on them was constrained to settle only in one direction, only in one geometric plane, only in the narrow shelf where the ring plane and the equatorial surface of the moon coincide. That constraint, that geometry, is what produced the shape. Not chaos, but order. Not the random scatter of impacts, but the precise selection of the Roche-limit's physics, choosing where the dust was allowed to rest and where it was not. So the next time you try to hold in mind the image of Saturn's rings, that flat, impossibly thin sheet of ice glittering in the sunlight, the system's most famous feature, visible through even a modest telescope from Earth, Consider that the rings are not entirely separate from the moons. Consider that Pan is sitting inside one of those rings every 13.8 hours, sweeping through the same material that surrounds it. The material that is still, in some slow and ongoing sense, becoming part of the moon, becoming the ridge, becoming the smooth white skirt that makes the silhouette so unmistakable. The rings are not a backdrop for the moons. The moons are, in part, made of the rings. The ring is the raw material, and the moon is what happens when the physics finds a shelf to lay the material on. Ring becoming moon, dust becoming ridge, the diffuse made local, the floating made settled, grain by patient grain, orbit by patient orbit, in the only geometry permitted, in the only plane available, in the only place where the tidal forces relent enough to let something small and quiet rest. There is a particular kind of tiredness that is not unpleasant. The tiredness that comes at the end of a day when something has been finished, when the mind has gone as far as it needed to go and can now begin to release. It is not the same as exhaustion. It is more like completion, the feeling of having arrived somewhere and being permitted to stop. Pan and Atlas arrived somewhere. After all those billions of orbits, after all those silent passes through the ring plane, after all those individual grains drifting in and settling onto the only shelf the physics provided, they arrived at a shape. Not a perfect shape, not a sphere. Nothing in this regime becomes a sphere. The gravity is too weak for that, but a characteristic shape, a shape specific to their situation, a shape that could not have formed anywhere else in the solar system, but exactly here, at the inner edge of Saturn's ring system, in the precise geometry of the ring plane, under the precise constraint of the Roche-limit. The ravioli and the flying saucer, the thin sharp skirt and the broad smooth saucer, arrived at over time so long that it dwarfs every human concept of patience. And the ridges are there now, fully formed or nearly so, as the Charnoz model suggests. The terminal ornaments. The process has run most of its course. The material that was available in those immediate lanes has been largely gathered in. The ridge is no longer growing rapidly, if it is growing much at all. It has arrived at its shape, and it holds that shape as Pan sweeps through the Encke Gap and Atlas circles at the A-ring's outer edge, orbit after orbit, the ring plane touching the equatorial ridge each time, the white ice renewing the surface, if not substantially building it higher. The brightness maintained even as the architecture settles into its completed form. There is something in that completion, too, that is worth resting inside. The process is not forever. It ran for a very long time, and it built something, and now it has mostly stopped building, and what it built remains. The ridge is a record, not of violence, not of catastrophe, but of patience, of accumulation, of the quiet geometry of dust, allowed to rest in the only place it was permitted to rest, over so much time that the nothings became something visible, something photographable, something that a spacecraft crossing the outer solar system could see and record and send back to Earth as one of the last detailed portraits it would ever take. And yet, to understand why those ridges are remarkable at all, to feel the true weight of their particularity, you have to stand them next to the other moons that orbit in the same crowded region, the other small bodies that also live in or near the ring plane, that also feel the same dust, that also carry some version of the same relationship to Saturn's gravity. And notice what those moons do not have. The skirt is not automatic. The skirt is not what happens whenever a small body finds itself near a ring. It is the outcome of a specific set of conditions, and the contrast with the neighbours makes that clear in a way that no description of Pan or Atlas alone ever quite can. Take Daphnis. Daphnis is a small moon, small even by the standards of this region, roughly 8 kilometers across, which puts it at something like a third the size of Pan. It lives inside the A ring, as Pan does, but in a different gap, the Encke Gap, a narrower clearing cut into the ring about 40 kilometers wide, sitting closer to the ring's outer edge. Daphnis was discovered by Cassini, not by any of the earlier missions, first identified in 2005 from images taken as the spacecraft settled into its long Saturn orbit. It is, in some respects, Pan's smaller cousin. Both are gap-embedded moons, both plough a lane through the A-ring, both exert gravitational influence on the ring material to either side of them, and both were eventually photographed in remarkable close-up detail during the mission's final years. But Daphnis does not look like Pan. Daphnis does not have Pan's smooth white skirt. And the reason Daphnis does not have that skirt is part of why Pan's skirt is worth understanding. What Daphnis has, instead of a skirt, is something dramatic and beautiful in its own right. It raises waves. As Daphnis orbits through the Encke Gap, its gravity tugs at the ring material to either side, not just laterally, pulling the gap edges into scalloped curves, but vertically, lifting the ring particles upward and downward out of the flat ring plane, raising rippled corrugations along the gap's inner and outer walls that can reach heights of approximately 1.5 kilometers. 1.5 kilometers of vertical relief, raised in a ring that is otherwise extraordinarily flat. And because these wave crests rise out of the ring plane into the sunlight at an angle, they cast shadows, long dark stripes visible in Cassini's images from certain geometries. A tiny moon 8 kilometers across, raising waves in a ring that is measured in tens of meters of thickness. And those waves, casting shadows, you can photograph from hundreds of thousands of kilometers away. Daphnis is remarkable. But it is not wearing a skirt. The reason involves, again, the Roche-limit and the specific critical density of these different worlds. Daphnis is small enough, and its circumstances particular enough, that the gentle equatorial accumulation that built Pan's ridge did not proceed in quite the same way. The skirt requires not just proximity to ring material, but a particular relationship between the moon's mass, its distance from Saturn, and the availability of fine particles moving at very low relative velocities in the ring plane. Conditions that aligned specifically for Pan and Atlas in a way they did not for Daphnis. The waves, not the skirt. The vertical ripples reaching upward, not the horizontal coat settling inward and outward from the equator. Same neighborhood, different outcome. And then there are Prometheus and Pandora. These two moons orbit not inside the A-ring, but on either side of the narrow F-ring, the thin, braided, chaotic ring that sits just beyond the A-ring's outer edge. Prometheus orbits just inside the F-ring, Pandora just outside it. They are the F-ring's shepherds. Their gravity on opposite sides of the narrow ring confines it, prevents it from spreading and dispersing, keeps it defined as a distinct feature rather than dissolving into the wider ring system or simply drifting away. Without shepherd moons, a narrow ring cannot maintain itself for very long. Prometheus and Pandora are why the F-ring is still a ring. They are interesting moons. Prometheus is elongated, irregular, something like 130 kilometers in its longest dimension, larger than Pan or Atlas, with a shape that has been described as a potato or a lumpy brick, or a somewhat rounded oblong with no clear dominant symmetry. Pandora is similar in its irregularity, smaller at roughly 80 kilometers in its longest dimension. Similarly lumpy and non-spherical. Both have cratered surfaces. Both show the complexity and irregularity that you expect from small bodies whose gravity has never been strong enough to impose a spherical shape. But neither Prometheus nor Pandora has an equatorial ridge. Neither has the ravioli silhouette or the flying saucer profile. They are potatoes next to Pan's tiny walnut. And the reason is that their location and their history are different enough from Pan's and Atlas's that the terminal accretion did not produce the same architecture. They shepherd a ring, but they do not orbit inside it. They interact with ring material gravitationally, but the geometry of that interaction, the relative velocities, the angle of approach, the Roche-limit constraints at their slightly different orbital radii does not produce a clean equatorial belt of settled dust. Their coats, to the extent they have coats at all, are not tailored into a skirt. Pan and Atlas, then, are not simply examples of a general principle, they are specific outcomes. They live in specific places, at specific distances from Saturn, with specific sizes and densities and orbital histories, and the combination of all of those specifics produced the ridge. The other moons nearby tell you what does not happen when any one of those specifics is different. The skirt is the answer to a very precisely posed question, and the question is, what accumulates on a small moon when it orbits at just the right depth inside the ring system? Over a very long time, under the Roche-limit's quiet rule about where dust is permitted to rest? The answer is a coat. Smooth, white, equatorial, patient, and it is an answer that only a very few moons in the solar system have given. That coat is, in the language of the researchers who first modelled it, a terminal ornament. Sébastien Charnoz used that word, ornament, and it is worth sitting with for a moment. An ornament is something added to a surface for decoration, something that beautifies without changing the underlying structure. But here the ornament is the planet's own material, laid on by the planet's own gravity, finished or nearly finished into its shape over time. The moon did not go out and collect it. The dust came to the moon because the moon was there, in the lane, and because gravity said, "This is the place." And now the ornament is done. The terminal ornament. The accretion that built the ridge has run most of its course. The immediate lanes largely swept clean, the material gathered in. What remains is the record of the process, worn around the equator like something earned through an incomprehensible patience. There is a word that the ancient Greeks used for the cosmos itself, cosmos, that meant simultaneously order and adornment, the decoration that comes from arrangement. The ring plane is cosmos in that sense. And Pan's skirt, Atlas's broad saucer, are cosmos worn on the body. The order made visible as ornament. Pan is named after the Greek god of shepherds, of the wild countryside, of the flocks that needed tending. The name was chosen deliberately, with full awareness of the pun it contained. This tiny moon shepherds the ring particles, keeps the Encke Gap open, tends the edges of its lane. Pan the shepherd. The name fits so precisely that it feels less like a label and more like a description discovered in mythology, as though the ancient stories were waiting, across all those centuries, for the right small moon to come along and give them a second meaning. A shepherd plods through the field, and the flock parts around him, and the grass grows where the flock has not grazed. Pan plods through the ring, and the ice parts around him, and the gap stays open where the dust has not settled. Atlas is named after the Titan who holds up the sky, the giant figure at the edge of the world, supporting the weight of the heavens on his shoulders. Atlas the moon sits at the A-ring's outer edge, near the Roche Division, and in one reading of its role it does something analogous. it helps define the boundary. It shepherds the A-ring's outer edge, its gravitational presence contributing to the sharp boundary that ends one of Saturn's most prominent features. The sky, in this case, is the ring, and Atlas stands at its margin, holding it in place. There is something quietly marvelous about the fact that both names are about tending, about holding, about the patient maintenance of a boundary or a shape. Pan tends the gap. Atlas tends the edge, and both of them, as they tend, are slowly covered in the material of the thing they tend, the ring ice settling onto their equators, the coat thickening over ages, the ridge growing until it reaches its terminal form, and then simply remaining, maintained now by the steady refrosting of fresh ring particles that keeps their surfaces bright without substantially building the architecture higher. The shepherd wears the fleece of the flock. And we would not know any of this, not the shape, not the skirt, not the mechanism, not the distinction between Pan's thin ravioli profile and Atlas's broad flying saucer. Without a spacecraft that travelled for 7 years to reach Saturn and then spent 13 more years circling it, taking pictures, measuring gravity, sampling particles, studying the magnetic field and the radio emissions and the ring structure and the small moons and the large ones, and that eventually, in its final year, turned its instruments toward the innermost, smallest, strangest members of the ring system to take the closest look anyone had ever taken. In the year 2017, Cassini did something that had never been done before and has not been repeated since. It flew through the region where Pan and Atlas live. The ring-grazing orbits began in late November of 2016. 20 orbits, each one carrying the spacecraft to a closest approach just outside the F-ring, the thin, braided ring beyond the A-ring's outer edge, threading Cassini through the territory occupied by Prometheus and Pandora and on carefully timed close approaches, bringing it near the smaller moons deeper in the ring system. It was an unprecedented configuration. For years, Cassini had orbited Saturn at safer distances, crossing the ring plane but not lingering within it, not flying through the immediate environment of the rings. Now, in the mission's final phase, the trajectory was tightened until the spacecraft was grazing, living in the ring neighborhood for stretch after stretch of orbit. On the 7th of March 2017, Cassini passed Pan at a closest approach of roughly 24,600 kilometers. This was the closest any spacecraft had ever come to Pan, and it is very likely the closest any spacecraft will come for a very long time, perhaps ever, in any human planning sense. The images that came back changed what scientists knew about Pan's shape. Before that flyby, Pan was known to have an equatorial ridge. Cassini had seen it at greater distances, the profile hinting at the skirt, but the details were not resolved. The texture of the ridge, the sharpness of its boundary against the cratered core, the smoothness of the accreted surface compared to the rougher, older terrain above and below, these were uncertain. At 24,600 kilometers, the ridge came into focus. The thin, sharp skirt was visible in detail. The distinction between the moon's older, pockmarked midsection and the fresh, smooth equatorial band was clear. The ridges that might represent successive layers of accretion, subtle grooves suggesting the coat was built gradually rather than all at once, were apparent. Pan looked, in these images, less like a lump and more like something assembled, something composed, something that had a history written in its profile. Scientists reached for the words they had, and the words they had were food words and furniture words and shape words: ravioli, dumpling, empanada, walnut, flying saucer. These were affectionate and accurate in the broadest sense, and they circulated widely because they captured something true about the visual impression. A moon that looks like pasta is a moon worth paying attention to. But the names were also, in a quiet way, a distraction from the mechanism, because you can call something a ravioli and stop there, satisfied with the recognition of a familiar shape in an unfamiliar place, without ever asking what the filling is or how the pasta got folded. The images from March of 2017 were images worth asking about. Not just, what does it look like? But, how did it come to look like that? And the answer, by then, was already available. The Charnoz model from 2007 was there to receive the images. The mechanism was understood, the Roche critical density, the ring plane orbits of infalling particles, the equatorial capture, the terminal ornament. The close flyby gave the mechanism a face. Then, on the 12th of April 2017, Cassini passed Atlas. Closer still, roughly 11,000 kilometers at closest approach. The flying saucer, resolved, Atlas came through in the images as a body with a broader, more distributed ridge than Pan's thin, sharp skirt. Where Pan's waist is cinched, Atlas's is wider, the saucer's rim flatter and more gradual in its slope from the equatorial bulge to the cratered terrain above and below. The same process, ring dust settling onto the equator under the Roche-limit's quiet permission, but the result shaped differently by Atlas's somewhat different size, perhaps its somewhat different history. The particular balance of factors that makes one small accreted world a ravioli and another a flying saucer. Both are skirts. But they are different cut skirts, and the images from April showed that difference in fine detail. By the time these images arrived on Earth, Cassini was in the final stretch. The ring-grazing orbits ended in late April of 2017. The grand finale began, 22 orbits in which the spacecraft dove between Saturn's innermost ring and the planet's upper atmosphere, a gap no spacecraft had ever crossed, measuring the ring mass and the planet's gravitational field and the structure of the inner atmosphere with a precision that required that proximity. And then, on the 15th of September 2017, the mission ended. Cassini was directed into Saturn's atmosphere deliberately, on purpose, a controlled plunge that burned the spacecraft up over the course of minutes in the uppermost cloud layers of the planet it had circled for 13 years. The reason for the controlled plunge was not carelessness or indifference. It was care. Cassini, having spent 13 years in the Saturn system, was running low on the propellant it needed to keep its antenna pointed at Earth and its instruments aimed where scientists directed them. A spacecraft with no navigational control drifting in the Saturn system would eventually collide with something, and the something it might collide with included Enceladus, the moon whose south pole vents plumes of water ice and organic molecules, whose subsurface ocean is one of the candidates in our solar system for an environment where life might exist, or might have existed, or might one day exist. And Titan, whose thick atmosphere and liquid hydrocarbon lakes make it another object of profound astrobiological interest. Cassini, built on Earth, carried Earth microbes despite every effort to sterilize it. A derelict spacecraft crashing into Enceladus would potentially contaminate the very environment scientists most hoped to someday examine cleanly. So Cassini was sent into Saturn instead, into the atmosphere that would burn it up, disintegrate it, disperse its atoms into the same planet it had studied for so long. The spacecraft became part of Saturn. And the last images it took of Pan and Atlas, in March and April of 2017 were among the last detailed portraits it took of anything in the ring system, parting gifts, sent back across 1 billion miles, arriving on Earth's radio telescopes as patterns of signal that scientists translated into the image of a small moon wearing a ring dust skirt. There is a quietness to that ending that suits the moons it was used to document. There was no catastrophe, there was no collision, no explosion, no dramatic failure. There was a spacecraft that had done its work, and that was guided, gently and deliberately, into the body it had come to know, so that the worlds it might otherwise have threatened could remain undisturbed. The same care that the ridge represents, patient, gentle, accumulative, was the spirit in which the mission ended. Pan circles the Encke Gap now, as it has for an incomprehensible stretch of time before Cassini was built, and as it will for an incomprehensible stretch of time after the last person who saw those 2017 images is gone. 13.8 hours per orbit. Roughly twice per Earth day. The gap edges scallop gently under its gravity, wavy and rhythmic, the same signature that Mark Showalter read in 1990 in 9-year-old Voyager images and translated into a prediction: there is a moon here, here is where it must be, here is the orbit it must follow, and then finding it. A moon located by the shadow it cast in a ring before anyone had laid eyes on it. Found by the shape of its absence, named for the shepherd it had already been before the name was given. Atlas circles the A-ring's outer edge at 137,000 and some kilometers from Saturn's center, 14.4 hours per orbit. Its broad white saucer rotating in the ring plane, its equatorial ridge lying precisely where the ring plane passes. The ice bright with the continuous light refrosting that keeps it among the most reflective objects in the solar system. Both of them lighter than water ice, because they are not solid rock, but porous rubble, fluffy aggregates of loosely bound material, like compressed snowballs that have never been under enough pressure to compact fully. Less than half the density of liquid water. Hold a bucket of water and imagine that the equivalent volume of Pan would weigh less than half as much as the water. And yet Pan is a moon. Pan has enough gravity to clear a gap. Pan is wearing a skirt of ice, it gathered itself, over time so long that our entire species, from its first stone tools to this moment, would be invisible in it, a thin layer of sediment in a much longer record. The ring plane from which the dust came is still there. The Encke Gap that Pan carved and maintains is still there, scalloped at its edges, the gap edge waves still propagating outward from Pan's gravitational tug. The A-ring's outer boundary that Atlas helps define is still there, sharp enough to measure. And the ridges are there, maintained if not built further. Refrosted by the ring ice that still drifts through those orbits, the bright white surfaces renewed even as the architecture holds its completed form. Somewhere in the ring system, Daphnis is raising waves 1.5 kilometers high in the walls of the Keeler Gap, casting shadows in the light of the distant sun. Prometheus is pulling streamers of material out of the F-ring with each close pass, leaving dark channels that close and refill as it moves away, braids and kinks in the narrow ring that make it look, in Cassini's images, as though someone has been playing with it. Pandora is circling on the other side, less disruptive, steadier in its shepherding role, keeping the F-ring from dispersing outward. These are not moons with skirts. These are moons with different histories, different geometries, different positions in the delicate accounting of Saturnian gravity. They are beautiful in their own ways. But they are not wearing the ring. Pan and Atlas are wearing the ring. And the reason, always, at the end of every explanation, the reason is the geometry. The flat geometry of the ring plane, the tilted not at all angle of those orbits, the Roche-limit's quiet insistence that fine particles approaching from the ring plane direction can only come to rest at the equator and nowhere else, because anywhere else the gravitational bookkeeping does not work out. The ring plane says, this is where orbits are. The Roche-limit says, this is where you may rest. The moon says, in the only way a moon can say anything, yes, and over time its equator accepts what is permitted, and the ridge grows, and the ornament is complete. It is not a loud story. Nothing about it requires drama. No impact, no explosion, no catastrophe. None of the violence that sculpted most of what we see when we look at the rocky bodies of the solar system, the cratered landscapes and shattered surfaces and collision-borne debris fields. This is the opposite of that. This is the story of what happens in the absence of violence, in the long quiet between events, when nothing is exploding and no large body is crashing into anything, and the only force operating is the gentle, persistent, patient pull of gravity on particles so small and numerous that they move as a fluid, as a fog, as the ring itself. The ring settles onto the moon wears the ring, and the two of them circle Saturn together. The ring plane and the equatorial ridge touching along the same invisible line, the same angle to the ecliptic, the same ancient flat geometry that has organized this part of the solar system since long before Earth existed in the form it has now. You are lying in the dark somewhere on a planet orbiting a star that is, from Saturn's distance, barely a bright star in the sky. A point of light around which that whole vast ring system and all its small moons and all their ancient ice dust skirts organize themselves patiently, geometrically, continuously. And from here, from the inside of whatever room you are in, whatever country, whatever night, you cannot see Pan or Atlas or the rings they inhabit. But they are there, circling, the ring plane touching the equatorial ridge at the same moment it has been touching it for longer than anything you can usefully imagine. If this slow kind of story is the kind that helps your mind release the day, if this is the kind of narration you want to drift inside, there are more stories here, slow and careful stories about the hidden mechanics of quiet things, about the shapes the universe makes when it is left alone long enough. They are here whenever you want them. And if you feel moved to say where in the world you are listening from tonight, I would genuinely like to know. The comments are there. I read them. There is something in knowing that someone in another country, in another time zone, in another kind of darkness, found their way to the same small moon and the same ring dust skirt and let it carry them somewhere quieter. That matters to me. But for now, you have done enough. The day has been whatever it was. The thoughts that were circling have circled long enough, and there is no more work required of you tonight. The Encke Gap is still open. The ridge is still there, white and smooth, precisely at the equator, precisely in the ring plane, exactly where the geometry said it was permitted to be. Pan sweeps through his gap. Atlas holds his edge. The ring plane is still. Good night from up here in orbit. I'll keep watch while you drift. Consider, for a moment, the other moons nearby. Daphnis lives in the Keeler Gap, not far from Pan in the outer A-ring, and Cassini photographed it too during those final orbits. Daphnis is smaller, roughly 8 kilometers across, a pale fragment, and what it does to the ring material around it is spectacular and violent in its own quiet way. Its gravity raises vertical waves along the edges of the Encke Gap, rippling walls of ring material that climb to perhaps 1.5 kilometers above the flat ring plane, casting long shadows like the folds of draped cloth seen from an angle. Those waves are beautiful. But Daphnis has no skirt. It has no smooth equatorial ridge, no evidence of the same patient gathering that shaped Pan's silhouette. The waves are a disturbance, a tidal conversation between the moon and the ring does not settle onto Daphnis in the same sustained, accumulating way. The shape Daphnis has is its own shape, not a coat. And then there are Prometheus and Pandora. These two shepherd the narrow F ring, one just inside it and one just outside, keeping that delicate braided ribbon from dispersing. They are elongated and irregular, something like potatoes, something like tumbled stones, and they do their shepherding work across millions of years without acquiring anything like the clean equatorial band that Pan and Atlas wear. Prometheus is roughly 136 kilometers at its longest, Pandora somewhat smaller. Neither has developed the pronounced smooth ridge that defines Pan's walnut profile or Atlas's saucer. They are shepherds, yes, but they are not gatherers in the same sense. The F-ring's material is structured differently, and the moon's positions outside the Roche critical density threshold do not produce the same accumulation dynamic. What Pan and Atlas carry on their equators is therefore not a routine outcome. It is the specific product of a specific geometry, a narrow set of conditions that had to be exactly met, the moon embedded within the ring plane aligned with the equatorial belt, the tidal balance delicate enough to let particles rest only in that one permitted zone. Slightly different location, slightly different mass, and you get a potato, not a ravioli. There is something else worth holding. The modelling suggests that what Pan and Atlas have accomplished is, in a sense, nearly finished. The lanes immediately around them have been largely swept clean. The material available to settle onto the equatorial ridge has been gathered over millions of years into the smooth band now visible in Cassini's portraits. And what remains drifting in the immediate vicinity is comparatively sparse. The ridge is not still building rapidly. It is more accurate to say it is a record, a nearly completed ledger of every grain that was permitted to settle there, and did. Charnoz and his colleagues used the word terminal to describe this in the careful, precise language of scientific papers, terminal accretionary ornaments. The process has run most of the way to its conclusion, and the ridge stands as evidence of all the settling that has already happened, a completed garment rather than one still being woven. The names, of course, were chosen with a kind of quiet intention. Pan takes his name from the Greek god of shepherds, of wild places and grazing flocks, of the tending of creatures through open land. The assignment is apt. Pan herds the ring particles, keeps the Encke Gap clear, maintains a kind of order that would otherwise dissolve. And Atlas carries the name of the Titan, condemned to hold the sky on his shoulders, that immense, patient, permanent effort of keeping a vast weight in place. Atlas the moon sits at the outer edge of the A ring and helps define its boundary, a gravitational anchor at the rim of something enormous. Both names suggest a labour that goes on without rest, without recognition, without an audience. Something that was always happening long before anyone thought to look. We looked because of Cassini. The spacecraft had been orbiting Saturn since 2004, threading through the system in a long, patient spiral of observations, building the most detailed portrait of the Saturnian system that had ever existed. By late 2016, the mission was entering its final phase. The ring-grazing orbits, 20 of them, from November 2016 through April 2017, brought Cassini skimming just outside the F-ring, diving through the region where the small inner moons move. On the 7th of March 2017, Cassini passed Pan at a closest approach of roughly 24,600 kilometers. The images that came back showed the ridge in a detail that had never been possible before. The thin, raised belt running precisely around the equator, smooth where the core was cratered, white against the dark of space. On the 12th of April, the spacecraft turned its cameras toward Atlas at a closest approach of roughly 11,000 kilometers. The broad saucer shape resolved clearly, the wider, smoother ridge, the flying disk profile that had only been hinted at in earlier observations from greater distances. These were among the last close portraits any human instrument would ever make of these two moons. The grand finale followed. On the 15th of September 2017, Cassini was directed into Saturn's atmosphere deliberately, a controlled plunge designed to destroy the spacecraft before its fuel ran out, and it could no longer be controlled. The reason mattered. Enceladus, with its plumes of water vapor rising from a subsurface ocean, and Titan, with its methane lakes and thick nitrogen sky, both offered conditions where life was not impossible. A dead spacecraft drifting uncontrolled might one day impact one of them, carrying terrestrial microbes, contaminating what the mission had spent 13 years trying to understand. So Cassini was sent into the planet it had orbited for so long, and it returned data all the way down until the signal ended. The Pan and Atlas portraits were, in this sense, among the mission's final gifts, images taken in the last months of a spacecraft's life, turned toward the smallest moons, the ones that looked like pasta, the ones that nobody had ever seen clearly before. There is something in that. Not pathos exactly, and not drama, but a kind of fidelity. The mission looked at everything it could, right to the end, and what it found in those last close passes was a pair of tiny moons wearing smooth white coats of ring ice, their equatorial ridges exactly aligned with the plane they had been orbiting inside for longer than the Earth has had oceans in their current configuration. The ridge is the ring made solid. The same gravitational arithmetic that keeps the ring from collapsing into a moon, that maintains the delicate Roche boundary between scattered ice and gathered world, is the arithmetic that built the skirt. The violence that created these moons, whatever shattering event left dense cores orbiting in the ring plane, has long since settled into something entirely gentle. Grain by grain, year by year. The dust finding the one place it was permitted to rest, and resting there. Nothing struck these moons to shape them. Nothing carved the ridge. Pan and Atlas accumulated their coats the way frost accumulates on a cold surface left long enough in the dark, quietly, without event, without announcement, until one morning the shape has changed, and there it is. And you understand that it has been changing all along, and you simply had not been close enough to see. The ring plane is still. The equatorial ridge is white and smooth and precisely where the geometry said it was allowed to be. If this is the kind of story that carries you somewhere quieter, if the slow accumulation of small and patient things is what your mind needs at the edge of sleep, there are more stories here. Unhurried ones, about the shapes the universe makes when it is left alone long enough. And if you feel moved to leave a word in the comments saying where in the world you are tonight, I would genuinely like to know. There is something in it. Knowing that someone far away found their way to the same small moon, and let it be enough. Pan sweeps his gap. Atlas holds his edge. The dust settles where it is permitted. Good night from up here in orbit. I'll keep watch while you drift.